Here we are at Multivariable Calculus, section 11.2 from your Edwards and Penney textbook, 3D vectors. Again, this is really just pre-calculus, but it's setting the stage for vector calculus later. Here we have three space, x, y, and z axes, and the coordinate, of course, has three components, x, y, and z. Now, if you rotate this space 90 degrees counterclockwise in the xy plane, and then 90 degrees counterclockwise in the yz plane, you get something that looks like this. It's the same space, but it's rotated. And some physics books draw it this way, so I just thought I'd let you see that. This way, your original piece of paper is like on the blackboard, and z is coming out towards you. Whereas in most math books, we have x and y on a piece of paper lying flat, and then the z-axis coming upward out of the paper. Now, distance in 3D is very similar to distance in 2 dimensions. If you have 2 points in 3 dimensions, you can think of them as the corners of a rectangular prism, a box. And so the distance we want is the distance between those 2 corners. And we'll label those 2 points with subscripts. And first what we're going to do is we're going to look at L, which is the hypotenuse of the triangle on the face, the front face of this box. And its legs are the difference in the y coordinates and the difference in the z coordinates. So just using our old friend the Pythagorean theorem, we get L squared equals the difference in the y coordinates squared plus the difference in the z coordinates squared. Now, L and D, and that little side up there at the top left side of the box, form another right triangle because the red line segment is perpendicular to the front of the box and therefore perpendicular to L. So the red line segment and the green line segment are the legs, and then D is the hypotenuse. So now we have D squared equals L squared plus the difference in the x coordinates, and then we substitute for L squared, take the square root and put it in alphabetical order. And so it's sort of an extended Pythagorean theorem in 3 space. Likewise, the midpoint is similar. We just take the average of the 3 sets of coordinates to find the midpoint of a line segment. Now in 2 dimensions, we have a circle, and we usually label the center HK, and if the radius is R, then here's our familiar equation for a circle. In 3 dimensions, again, this is really just based on the Pythagorean theorem, or the distance formula rather, because we're saying that the distance is all from the center to any point x, y is always r. So it's the same kind of thing with the sphere. We'll call the center HKL and the radius still r, and so the equation of the sphere just adds the z component the same way it did with the distance formula. Unit vectors. We looked at them in 2 dimensions. In 3 dimensions, we have 3 of them, I along the parallel to the x-axis, j parallel to the y-axis, and k parallel to the z-axis, each 1 unit long, hence the name unit vectors. Now here we have a vector in 3 space, and it has 3 components. The point, if the vector is drawn in standard position with its tail on the origin, then the point ABC also names the vector, except that we use chevrons. Or we can think of it as the sum of 3 vectors. Here I have the vectors lined up with the dotted lines. If I scoot the vector AI over so that it's lined up with the x-axis, you can see that if you followed AI and then BJ and then CK, if you added those 3 vectors together geometrically, the resultant would be V. And so we can still write vector V in terms of ij and k this time in 3 dimensions. The dot product. Given vector A denoted that way and vector B denoted this way with the subscripts, turns out that A dot B, well, by definition, A dot B is the product of the first components plus the product of the second components plus the product of the third components. And notice that these are all numbers. So what you get when you dot 2 vectors is a real number, not a vector. Now there's another multiplication called the cross product, which we'll look at in the next section. And the cross product is a different way of multiplying vectors that creates a third vector. Now you might think, well, what good is the dot product? Well, here's a picture of A and B, two vectors in 3 space. And there's an angle between them. And it turns out that the dot product is equal to the length of the vectors times the cosine of that angle. And so the dot product is handy in finding the angle between two vectors. So let's show you why that's true, kind of briefly. Let's draw a third vector connecting A to B. And so that I don't have to keep typing in the absolute value, let's just let A, B, and C, without bold, be the lengths of the 3 vectors. And using the law of cosines, C squared, the length of C, is equal to A squared plus B squared minus 2AB cosine theta. Also notice that A plus C is equal to vector B, and therefore vector C is the difference between the 2 vectors, if we just subtract vector A from both sides. And so the length of C is equivalent to the length of vector B minus vector A. And if we square both of them, then they're still equivalent. So using the components of vector B minus vector A, we can get C squared equal to the square of the individual components. So now we've got 2 expressions for C squared. And so on the next page, we're going to set those equal. Okay, so on the left, the length A, remember A and B were the lengths of vectors A and B. And so we can get those lengths squared by squaring the individual components. And then on the right side, I just multiplied those out, expanded them. And that looks pretty horrible, except that lots of stuff cancels. Now we're going to divide by -2, and we get this. And then there on the right, you should recognize the dot product. And so rearranging it alphabetically, we have the equation that we wanted to show was true. Rearranging that, we can solve for cosine theta, and this is the form that's used mostly because we're usually using the dot product to find the angle between the 2 vectors. Now notice that if A dot B is 0, then that means cosine is 0, and therefore we have a right angle. And vice versa, if we have a right angle, then the dot product will be 0. Direction angles. Vector V forms 3 angles with the 3 axes. We're going to call the angle made with the x-axis alpha, and the one made with the y-axis beta, and the one made with the z-axis gamma. Recall our formula from the last example. And so to find alpha, we're going to dot V with I, and notice that we don't have to divide by the length of I because the length of I is 1. So we get a nice little easy formula. Likewise for beta, we're going to dot with J, and for gamma, we're going to dot with K. Projections. Let's say we have a light shining perpendicular to that blue vector. Then basically there's a projection of the red vector onto the blue vector, like a shadow. And that's what it's called, the projection of A onto B. Now let's say the angle there is theta. Then just using simple trigonometry, the length of that shadow is the length of A times the cosine of theta, because it's the adjacent leg of that triangle. And so the projection of A onto B, notice the B is the subscript here. It's read projection of A onto B. Then is that length times multiplied times vector B. And if you just look at the length of it, that's called the component of vector A onto B. And if you divide, this is kind of weird, but watch what happens. If you divide and multiply that quantity by the length of vector B, you get the dot product in the numerator. So now we've got a shortcut formula to find the component if you need a projection for some reason. And finally, work. Remember, work is force times distance. In vectors, it's the dot product because work is numerical, it's not a vector. So for example, here we have a little boy pulling a sled, and the vector shows the way he's pulling it, and then this vector shows the way he's walking. And let's put some numbers to this. Let's say the kid is pulling with a force of 25 pounds at an angle of 45 degrees and travels 1 mile. How much work does he do? 25 for the force vector, 45-degree angle, and now he's going to go 5,280 feet. Because remember, work, we usually use foot-pounds, so change the mile into feet. Now, vector F is the cosine times I. If we change this into a sum of the two perpendicular vectors I and j, then the I vector component would be multiplied by 25 cosine 45, and the j component would be 25 sine 45 degrees. And then the distance is just along our x-axis. This is two-dimensional, not three-dimensional actually, although the formula works for 2 and 3-dimensional problems. So then the distance vector is just 5280 times I. So we dot those two together, and notice that the j component of d is just 0. And we get approximately 93,338 foot-pounds. Okay, now I've done a bunch of examples from your book, but I'm going to put them in a second video because some of you may not need the examples and this video is getting a little long. So the second video will have examples.